Hello and welcome to the efficacy of sub 75 horsepower diesel engines with DEF systems implemented. I am Brandon O'Neill and my group members are Nathan, Jeffrey, Edward, and Alexander. This project was inspired by the regulations the EPA imposed in 2010 that intended to curb the emissions of nitrous oxide by diesel engines across the country. They made these rules only apply to engines above 75 horsepower, and we wanted to know if the systems would have had a contributing impact on the environment, where they were installed in engines of all sizes. The system works by injecting diesel exhaust fluid, or DEF, into the exhaust stream. It has passed through two other emission-reducing components, a DOC and DPF. The mixture then passes through another catalyst where it's neutralized and finally passes into the atmosphere. The test was designed revolved around a mimicked DEF system that was modified for a small displacement diesel engine. Using a gas analyzer capable of reading NOx levels in parts per million, the engine would be run at 3 different RPMs with corresponding loads. This data would be collected with the analyzer in these three ranges with and without the DEF system installed, and the results of the similar ranges will be compared to see if the system did in fact lower the NOx emissions. The dyno setup. To apply load to the engine and monitor temperatures in RPM, a water brake dynamometer was installed. This uses water to resist the power of the engine. It also breaks the mechanical powertrain from the engine to the track so the engine can get to a higher RPM without moving the track at all and making it much easier to collect data. This is also a lot safer than having it connected to the track.
For our definition system, we modified a Faurecia DOC, or diesel oxidation catalyst, to be fitted with V-band clamps in order to easily integrate it into the emission system. The attached DOC was fed DEF fluid to bind with any NOx emissions which may be emitted from the engine. We encountered a budget constraint with the DEF system as some of its components, such as the SCR, or selective catalytic reduction, and DEF injector, which can cost upwards of $1,000 for each component. The risks involved in this test were numerous but easily mitigated. Moving engine parts were made known to all members of the test group, and hot components were isolated. To reduce the possibility of exhaust inhalation, the tests were performed outside, and eye and ear protection was worn throughout the operation, and in case of fire, extinguishers were kept within reach at all times and when a risk was imposed during component manufacturing. This is the graph of the baseline data for the idle RPM run. It breaks each of the varied gases using the axes on the left for carbon oxides and the right axis for NOx emissions. The beginning of the NOx curve is still slightly representative of the engine reaching full operating temperatures. That's why it is slightly skewed upwards over the course of the run.
This is the baseline data graph at 1600 RPMs without the DEF system. It displays similar emissions levels to the first graph, but without as much fluctuation. This is the graph of the high load and high RPM emissions data for a natural exhaust run. This run saw increased levels of all gases except carbon monoxide. It also shows the fluctuation in levels of NOx. This is the most likely due to the engine reaching a higher temperature and remaining within a tighter RPM range the entire time. And lastly, here's the graph of the test we ran with the DEF system installed at idle RPM. There's a significantly high level of hydrocarbons after the introduction of the DEF, which is to be expected. Unfortunately, though, the level of NOx did not decrease and average within 1 part per million of the baseline idle data. The results clearly demonstrate the emission system did not work as it was initially predicted. Many of the reasons for this can be attributed to the manufacturing issues with fabricating the DOC system. Some of the mixing chambers had been improperly welded, which caused issues with the atomization of the DEF fluid. The increased hydrocarbon levels from the DEF system are caused by what is known as ammonia slip, in which ammonia escapes the rear of the tailpipe due to higher levels of DEF fluid in the system.